Okay, so in this video, we're going to talk a little bit about Chapter 6 and chemical composition. So the idea is we're going to learn a little bit about the mole, Avogadro's number, and kind of how we can actually count atoms and represent them on the real-life scale. So we're going from this little teeny tiny atoms all the way up to what we experience in the lab. So here are your learning objectives for Chapter 6. Basically, it's a lot more unit conversion, just like Chapter 2 was. So it should be something that's pretty familiar to us. We're just going to learn some new conversion factors. So chemistry is kind of wonky a little bit. So the kind of difference in a way between the way expert chemists think about chemistry versus the way a lot of people who are learning chemistry for the first time think about chemistry is chemists are very easily able to move between these different levels and think about things in terms of individual atoms versus, grams of things, which you can see with your eyes, versus writing the chemical equation for all of this, right? So this is something that you have to kind of get used to. It's part of the thinking process about chemistry. So far, we've only really been looking at things from the submicroscopic level. So we're looking at things that can't even be seen with a regular microscope. So this is going to be like atoms, ions, compounds, like the chemical reactions physically happening between one molecule and another molecule kind of a deal. Again, one of the toughest parts about chemistry is learning to move between different levels of scale, right? So we're thinking about this submicroscopic level, the level of chemistry that happens at individual atoms or even like those electrons and protons and neutrons that make up atoms, right? So this is the scale we've been working on this far. We've been thinking about individual atoms, how do we write the chemical formulas of compounds, chemical equations, things like that. However, we also need to be able to move to the macroscopic level of chemistry, right? So this is the scale of chemistry where we're working in the lab. So rather than thinking about individual atoms, we're thinking about grams of a compound, like when we measured about 2 grams of our sand and salt mixture the other day. It's a bigger scale. We weren't counting all of those little individual particles the entire time, right? Even though we wanted to track and make sure we were keeping every single salt ion, every single sand particle, we wanted to track all of those, but we weren't doing it by counting individual atoms. We were doing it by taking the mass and seeing how much we had overall rather than each individual atom. So that's the macroscopic scale. This is our lab scale level chemistry. But the other kind of thing we have going on here is we also have the symbolic form of chemistry. So this is the way we represent chemistry happening when we want to talk about it or pass something on to each other, right? So this is things like writing chemical formulas, chemical equations, ball and stick models, space filling models, all those models that we use. That's a symbolic way to represent the chemistry that's happening in the end. So we got to kind of move between this submicroscopic and this macroscopic level of chemistry, and what we do is we use information from how we symbolically write things down to do this. So this chapter actually focuses on how to move between the submicroscopic level to the macroscopic level using information from the symbolic level. What does that even mean? What did I just say? So basically, we need to go from looking at individual particles, individual atoms, individual ions, compounds, molecules, to large lab scale amounts of particles. And we actually have to use the information contained in the chemical formula or the chemical equation to do this. So this chapter focuses on how to use the information contained in the chemical formula. But when we get to Chapter 8 in a couple weeks, then we'll focus on how to use the information from a chemical reaction. So let's get into it. How do we actually go from individual particles to scale up to what we can actually see? So you can kind of think of this as like counting something by the pound, okay? So we often find it useful to count an amount of mass, not by actual individual items, okay? So if you go to the hardware store, you might find that if you want to buy nails in bulk, you're going to buy nails by the pound. Or if you go to the grocery store, you might buy like bulk coffee or something like that too. So we're going to buy something by the pound. You're not going to go to the store and count individual nails or individual coffee beans to get how much you want. That's not very useful, right? It's not very practical. It's going to take us a lot of time. Could you imagine going to the hardware store and there's about 50 nails and a pound of nails, depending upon the size of nail. Could you imagine the cashier just going 1, 2, 3. I mean, back in the day, I remember buying Tootsie Rolls by the penny and they had to do that. Did the cashiers hate us? Yes, when we bought $1 worth of Tootsie Rolls, right? The way they could have saved themselves some time is that they were measuring by the pound. So you might go to the hardware store, the grocery store, and you might find someone, measuring things by the pound. Instead of that, we buy our fruits and vegetables that way too. Some of them it's easier to count by the individual item. Sometimes it's easier to buy bulk and go by the pound. It just kind of depends upon the scenario, the situation we're talking about. This is also like buying a dozen eggs rather than picking out 12 individual eggs. We're kind of calling a pound a certain amount of mass, whereas, we're calling 12, or we're calling a dozen 12 of something, okay? Could you imagine literally going to the grocery store and waiting for everyone to pick out the exact number of eggs they wanted? And count out 12 eggs, look at each one, determine if it's cracked. I would lose my mind. I couldn't handle it. Are you kidding me? There's no use in doing things like this. It's much easier to buy things in familiar groups and to work with things in familiar groups than it is to worry about trying to keep track of every little individual thing that we do, okay? So we do the same thing in chemistry when we work in the lab. So when we're working on the experiments in your lab notebook, there was a lot of pre-calculation done to determine how much exactly you should be measuring. So we did the calculation before we wrote the lab book, before we gave it to you to say, this is the ratio we're gonna need on that macroscopic scale. So for example, as I mentioned before, in that separating a heterogeneous mixture lab where we were separating sand and salt, we were really trying to track every single particle, but we were measuring in grams. We weren't counting particles. So it's that same kind of deal. It's kind of been done in the background for you, but we're going to bring it to the forefront. You're going to learn how we kind of come up with some of these ideas. Okay, so how do we actually count these atoms on the macroscopic scale? So we use something called a mole. Yes, it sounds just like the animal. No, it's not named after the animal. Mole, like molecule. Mole, we could call it, but it's a mole. That's the way it's spelled. Yes, we often use the mole as a mascot in chemistry. I have great memories of Mole Day at Western where we had a song we would sing and we had like little teeny tiny moles. And one year I won the Pin the Tail on the Mole contest and got to be the Mole Queen. So I was very excited that year, let me tell you. So we usually celebrate on October 23rd. 10/23. So we usually celebrate Mole Day on 10/23. It's kind of a little almost inside joke with chemists. So we're going to talk about something called the mole. Well, what do I mean? Okay. This is like a dozen atoms. A dozen of atoms. It's not 12. 12 is always a dozen. If you have a half dozen, you have 6, right? So 12 is always a dozen. So the mole is like having a dozen for atoms. Like we don't want to count those individual atoms. It's going to take us forever. And we don't have scanning electron microscopes to be doing this with all the time, right? We can't count individual atoms. So how do we kind of track these things? How do we think about it? Well, 1 mole of anything, so a dozen is 12. 1 mole is 6.022 times 10 to the 23rd of something. So this could be atoms, ions, compounds, molecules, eggs, nails, dogs, cats, cars, houses, what have you. You know what I mean? If you have 6.022 times 10 to the 23rd of something, you have 1 mole of that. Now, does it make sense for us to have 6.022 times 10 to the 23rd eggs? No, that's why we count eggs by the dozen, because it's practical to do that. We're counting things like atoms and particles by the mole because it's practical to use such a large number to count something so teeny, teeny, tiny. So it's an extremely large number because atoms are so small. It's based off of the number of atoms in 12 grams of carbon-12. So that's where the number's coming from. It helps lots of things fall in place that we based it upon this. So we often call this Avogadro's number. So this is Avogadro's number. It's 6.022 times 10 to the 23rd. It's named after Amadeo Avogadro. So like, what a name, my dude. What a name. I think I spelled it wrong on the screen, but what a name, my guy. So you know, just like we can say like 6 eggs is a half dozen, we can kind of use Avogadro's number to determine how many atoms of things we have relative to a mole. So like if I have so many atoms, how many moles do I have? Or if I have this much of a mole, how many atoms does that represent? So we're going to try to count our atoms by the mole here. So we use Avogadro's number to mean 6.022 times 10 to the 23rd things equals 1 mole. Please don't ask me why, because I have never understood this. Maybe there are elder chemists out there that understand better, but the abbreviation to mean mole is MOL. Just like we use G to represent gram, MOL is how you shorten mole. It's not M, it's MOL. So all we do is cut off the E. I always thought that was kind of silly. I didn't know why we couldn't just write the E as well, but remember, we're lazy and we don't want to have to write more than we have to. So let's go ahead and work through these two problems that you see on your screen. Okay, so we're going to go ahead and work through the first practice problem on your screen here. So we just want to know how many atoms are in 2.6 moles of nitrogen. So if I want to know how many moles or how many atoms are in 2.6 moles of nitrogen, I'm going to go ahead and think about what we got going on. So I know that I have 2.6 moles of nitrogen as written in the problem, and I'm looking for atoms. So I'm trying to go from moles to atoms. Well, I do have a number that relates moles to any number of individual things, which is Avogadro's number, which is 6.022 times 10 to the 23rd. Let's say atoms equals 1 mole. Okay, so 6.022 times 10 to the 23rd atoms equals 1 mole. So I'm going to go ahead and set up my conversion chart here. So 2.6 moles of nitrogen. If I want to use my conversion factor, remember I'm looking for moles to cancel out, so I'm left with atoms. So I'm going to put 1 mole on the bottom. And then I'm going to put 6.022 times 10 to the 23 atoms of nitrogen on top. So looking through what I've got going on here, let me just double check. It looks like I have moles of nitrogen on top, moles of nitrogen on bottom. Those are going to cancel out, so we're left with atoms of nitrogen. That's what we're looking for. So I'm going to go ahead and multiply this out. So 2.6 moles of nitrogen actually gives us 1.6 times 10 to the 24th atoms of nitrogen. Okay, so 1.6 times 10 to the 24th atoms of nitrogen. This really should have 2 sig figs because 2.6 only has 2 sig figs in it, and Avogadro's number is never going to interfere with our significant figures. So our first problem here, we have 1.6 times 10 to the 24 atoms of nitrogen. And one thing I really want to caution you with as we're starting to use Avogadro's number is it's going to be kind of tough to always remember that you've got that second half of scientific notation. So you're going to have to notice it when it's in your calculator, and you're going to have to make sure you're writing it down every step of the way. Sometimes you can just kind of slip of the hand, forget, and only write the decimal portion and not the exponent portion with like times 10 to the whatever. So I just want to caution you right now, you have got to be certain that your answers are written in the proper manner. All right, so let's go ahead and do the second problem here. So what we want to know is how many moles of nickel are contained in 12.04 times 10 to the 23 atoms of nickel. Well, it looks like here I have atoms, and it's saying how many moles. So I'm trying to go from atoms to moles. And there is a relationship, of course, we have between moles and any individual number of things, which is Avogadro's number, our bestie Avogadro. 6.022 times 10 to the 23rd atoms is 1 mole of atoms. Okay? So now that I know this, and I'm trying to go from atoms to moles, let me go ahead and set up my problem. 12.04 times 10 to the 23 atoms of nickel. And of course, I'm trying to go from atoms to moles, so I'm looking to cancel out atoms, keep moles, so I'm going to put atoms on the bottom to cancel out the fact that atoms is already on the top, and then I'm going to put 1 mole on the top. So I'm going to put 6.022 times 10 to the 23rd atoms of nickel on the bottom, and I'm going to put 1 mole of nickel on the top. So if I go ahead and I multiply this out, I'm going to take 4 significant figures because 12.04 has 4 sig figs. So that leaves me with 1.999 moles of nickel. Okay, so it's pretty straightforward. You just got to make sure you're setting your conversion factor up right. So basically, Avogadro's number, as I've been talking about all of this grand information about scale and moving between things, it's just another conversion factor, like 12 inches in a 12 inches in a mile, 12 inches in a foot, 5,280 feet in a mile, kind of a deal. Same thing going on here as we're trying to count atoms by the mole. We're just using Avogadro's number as a new form of conversion factor. This conversion factor just happens to help us move between that submicroscopic and that macroscopic level. So I've left you with some practice as well. Okay, so we've kind of talked about the mole a little bit. It kind of feels a little arbitrary. You know what I mean? Okay, you know, I've got a mole. So what, right? Well, yeah, it helps us talk about large numbers of atoms. Sure, but it's not like you can go in the lab and you can measure 3.5 moles of helium or something, right? So we actually need to use some of the information in our toolbox to measure atoms by mass instead, so that we can measure the amount that we need if we go into the lab, right? So instead of measuring 3.5 moles of helium, we could measure a certain amount of grams of helium, for example. So how do we do this? We are going to use the molar mass. So the molar mass relates the mass of 1 mole, or the mass to 1 mole of atoms of that element, okay? So this is actually going to be the same value as the atomic mass you see on the periodic table. However, in this case, it means something a little bit different. So because of how we defined atomic mass, and because of how we chose to define a mole, they basically line up in this manner on the periodic table, where we can say that 1 atom of chlorine, for example, has an atomic mass of 34.35 AMU. However, if I want to think about a bunch of chlorine atoms on the large scale, I could say that 1 mole of chlorine atoms weighs 35.45 grams. So it's a relationship of an amount of mass to 1 mole of that kind of atom. So the unit is grams per mole. So if I have chlorine, I have 35.45 grams for every 1 mole, grams per mole. So for example, carbon is 12.01 grams in its atomic mass, or 12.01 atomic mass units, or you can think of it as 12.01 grams for every 1 mole. And then every 1 mole is 6.022 times 10 to the 23rd atoms. So now we're starting to build this relationship between counting the number of atoms versus counting a certain number of grams, okay? And the mole kind of gives us a standardized way to compare a certain number of atoms of one kind of element to a certain number of atoms of another kind of element. So this is why we use the mole as this kind of intermediary step, because it can help us compare 2 things a little bit more directly, because we know that we're not kind of taking anything into consideration except for the number of atoms we're counting. So let's go ahead and work through some examples of how we might go back and forth between the number of moles we have and the amount of grams we have, as well as throwing in the number of atoms in there. Okay, so the first example you see on your screen says how many moles are in 0.25 grams of ruthenium, okay? So throughout the video today, I'm going to be using the same periodic table you expect to see on your exam and with your Chapter 6 homework. So if you're not using this periodic table, you run the risk of them having rounded something different in their background information of creating the periodic table than what I did. Not when I did to create this periodic table, but you're basically going to run into some backgrounding issues if you choose not to use the periodic table I provided for you. So I want us to get some practice with that periodic table, so I'm going to show it to you in the video today. Okay, so now we're actually going to work through the first problem you see on your screen here. So we want to know how many moles are in 0.25 grams of ruthenium. So, let's go ahead and work through this problem. So it's asking us, how many moles are in 0.25 grams of ruthenium. So it looks like how many moles are in 0.25 grams of ruthenium. So I have 0.25 grams of ruthenium, and I'm looking to move to moles. So I'm trying to go from grams, which is mass, to moles. So I need a relationship between mass and moles. Well, if I'm thinking about grams and moles as a relationship, that's going to be the value that you can get from the periodic table. Let's go ahead and check that out. So, that being said, if I go to my periodic table, I find that ruthenium has a molar mass of 101.07. So that's 101.07 grams per mole. So this is 101.07 grams for every 1 mole. And now remember, we're getting this information off the periodic table specifically for ruthenium. So ruthenium is going to look different than cesium, it's going to be different than boron, it's going to be different than iodine. They have all different sizes and masses. So remember, you're getting each individual value for whichever kind of element you have off the periodic table when it comes to the molar mass. So I got the 101.07 grams equals 1 mole from the periodic table, okay? So let's go ahead and use the information we have to solve the problem. So if I have 0.25 grams of ruthenium, and I know that I have 101.07 grams for every 1 mole. I want to make sure I'm setting this up so my units cancel out. So I would have 101.07 grams of ruthenium on the bottom for every 1 mole of ruthenium. I'll go ahead and put that on the top. And then when I go ahead, I multiply this out. What I end up getting is 0.0025 moles of ruthenium in 0.25 grams of ruthenium. So again, we're just trying to relate grams to moles, moles to grams, back and forth. These are actually very useful calculations that we do all the time. A lot of times we're trying to figure out, like how much of something do I need for the lab? So I could say, I know when I'm kind of working through my problem, I have it figured out that I need 3.1 moles. Well, again, I'm not going to go in the lab and measure 3.1 moles of something. I'm going to want to know how many grams I need to measure. So this is a calculation chemists do often. It's something we have in our back pocket that we can take out at any notice to be able to do this kind of calculation. It's pretty important. So keep that in mind. But we are going to go ahead and work on the next problem that you see on your screen. We want to know how many grams make up 3.10000 moles of cesium. Okay, so it looks like our problem here is asking us about 3.1 moles of cesium, and how many grams is that? So here it looks like we're going from moles to grams, which is again mass. And remember, if we're thinking about mass and mole ratios, we're going to need to use our periodic table. So I'm going to go ahead and I'm going to find the molar mass of cesium. So the molar mass of cesium is 132.91. So cesium's number 55 in the bottom left-hand corner of your screen. So it's 132.91. So that's 132.91 grams of cesium for every 1 mole of cesium. Okay? So now that we have information, I see that I'm going from moles to grams. I have a relationship between moles and grams. So let's see what I can do. So if I have 3.10000 moles of cesium, I have a relationship between moles and grams of cesium. So if I start with moles, I'm looking to move to grams. That means I want to make sure I'm canceling moles out. So I'm going to put 1 mole of cesium on the bottom to cancel out my unit up here at the top. And then I'm going to put my 132.91 grams of cesium on the top. So if I check this out, I can check that my units cancel. I've got moles of cesium on the top. I've got moles of cesium on the bottom. And if I multiply this out, I find that I have 412.021 grams of cesium for every 3.1 moles of cesium. Okay. Let's go ahead and keep moving on. We'll do the next 2 problems as well. So the next 2 problems try to relate how many atoms make up a certain number of grams. So while this is important, a lot of times we're working with moles and things like that. We're not usually trying to move between numbers of atoms and moles and grams and things like that. So it's important along the way to remember to use these steps, but I think number 1 and number 2 are more important form of calculation by far. So, but we'll go ahead, we'll work through number 3. Number 3 says how many atoms make up 0.165 grams of boron. So it looks like I have 1.65 grams of boron, and I'm looking for a number of atoms. So I'm trying to go from grams, which is a mass, to a number of atoms. So the thing that I kind of see here is that I'm trying to compare mass and atoms. Well, we don't really have a direct comparison for that, right? We know atoms and moles, and we know mass and moles. We don't know atoms and mass. But, however, did you hear something there? I know mass and moles, and I know atoms and moles. Well, let's try using the mole as an intermediary step to get from grams to moles, and then I can go from moles to a number of atoms. Let's try that. So, if I'm even thinking about relating mass and moles, I'm going to go ahead and pull the molar mass of boron from the periodic table. So the periodic table shows me up here that boron, number 5, has a molar mass of 10.81. So boron has a molar mass of 10.81 grams for every 1 mole of boron. And then I'm also thinking about the fact, too, that I'm trying to move from atoms, or from moles to atoms, from grams to atoms in a more roundabout way. And I know that every 1 mole of anything is 6.022 times 10 to the 23rd of that thing. And well, in this case, we want it to be atoms. Okay? So it looks like we have some information here. We're trying to go from grams to atoms. I have a relationship between grams to moles. I have a relationship between moles to atoms. So it kind of is starting to look like I have all my moving parts in place. So I'm going to scroll up just a little bit here so that I have just a little bit more space. So I have 0.165 grams of boron. Well, I want to get rid of grams. I know that for a fact. I'm trying to go from grams to something else. So let's use the molar mass to get rid of grams. So I'm going to put 10.81 grams of boron on the bottom for every 1 mole of boron. So if I check out where I'm at, I've got grams of boron on the top, grams of boron on the bottom. So therefore, I am now left with the unit of moles of boron, okay? Well, I do have a relationship between moles and numbers of atoms, so I'm going to go ahead and leverage that information and use that here to solve my problem. So if I know 1 mole of anything is 6.022 times 10 to the 23rd of that thing, and I want 1 mole of boron atoms, which I'm putting 1 mole on the bottom so it cancels out, because I don't want moles, I want atoms. So now I have 6.022 times 10 to the 23rd atoms of boron. Okay, so I'm going to double check my units again. Grams of boron on top, grams of boron on bottom, those cancel out. Moles of boron on top, moles of boron on bottom, those cancel out. I'm left with atoms of boron, which is what I'm looking for. So I'm going to go ahead, I'm going to multiply this out, and I'm going to get 9.19 times 10 to the 21st atoms of boron. Okay, so it kind of takes a little bit more work, a couple more steps in there, a little bit more thought process to get from atoms to grams or to get from grams to atoms. However, in the end, it pays off because we're moving from that submicroscopic level where we're counting individual atoms on up to working with an amount of grams of something that we can actually study in the lab. So let's go ahead and work through the last problem that we see on our screen here. We want to know how many grams are in 3.014 times 10 to the 25th atoms of iodine. So I'm looking at this problem, it looks like I'm going from atoms of iodine to grams. So atoms to grams is our goal, which is mass. Okay, so if I'm going from atoms to grams, I know again that I don't really have a direct comparison, but I do know how many atoms are in 1 mole. I know that there are 6.022 times 10 to the 23rd atoms for every 1 mole. And I also know that I can relate moles to mass. I can relate grams to moles using the molar mass. And in this case, if I have iodine, the molar mass is 126.90. So that's going to be number 53 on your periodic table, 126.90. So that's 126.90 grams of iodine for every 1 mole of iodine. Okay, so it looks like I'm going from atoms to grams. I have a relationship between atoms and moles. I have a relationship between grams and moles. So I'm kind of looking like I can get there. So let's start to set this up. So I'm going to scroll up again for just a bit more space. So I'm starting with 3.014 times 10 to the 25th atoms of iodine. And then I'm going to go ahead and leverage Avogadro's number. I'm going to say, okay, if I know that I have 3.014 times 10 to the 25 atoms, well, I can figure out how many moles I have. Let me do that step. So I would try to cancel out atoms. So I would want to put the number containing atoms down on the bottom here. So I would put 6.022 times 10 to the 23rd atoms of iodine for every 1 mole of iodine. Okay, so I'm going to keep going with my multiplication. This is all 1 line. I'm just running out of space because I have big handwriting. So I've got this, I'm looking at this here. If I want to check out my units, I've got atoms of iodine on the top. I've got atoms of iodine on the bottom. So those are going to cancel out. So I'm left right now where if I multiplied this out, I would be in atoms of, or moles of iodine. So right now I am in moles of iodine. I've gone from atoms to moles. However, remember, we're not stopping at moles this time. We want to know how many grams of iodine represent this number of atoms. So in that case, I am going to use my molar mass that I found on the periodic table to complete this conversion. Right now I have moles on the top, so that means I'm going to want to put moles on the bottom to cancel out. And I'm going to put my 126.90 grams of iodine on the top. So if I go ahead, I multiply all of this out, I find that I have 6,351 grams of iodine. Okay, so that's kind of an idea of how we can go back and forth between counting mass, counting atoms by mass, figuring out how many atoms are in a certain amount of mass. But again, it's kind of a little bit more useful, and what we tend to do more often is go in between moles and grams. So I've left you with some practice, of course, on your screen. So go ahead and work through those. Let me know if you have any questions. It's a good time.